So, welcome to the fourth module on VLSI testing of the course on optimization techniques for digital VLSI design. So, as you have seen in the first three modules, Dr. Chandan Karfa has taught you about what are the optimization techniques which caters to the design part of the VLSI or the digital design flow. But once a chip has been fabricated or it has been gone through all the design steps and it has been sent for the fabrication, then after it comes out from the fab lab, it has to be tested. Because the idea is that in case of VLSI or in case of digital design at the higher level of integration, so what happens basically is a very large factor of the circuits may not be compared to traditional systems, more large number of circuits may have some inbuilt manufacturing faults. So, all circuits has to be tested before they are sent to the market. Otherwise, there can be issues like there can be system failures, or you will be sending a chip to the customer which will be not working properly and the system may have failures. So, to avoid all this, we try to test all the parts or all the chips before they are sent to the market. So, as we are discussing continuously in the course that this is actually the optimization techniques on basic CAD flow. So, these first two lectures basically 1 and 2 in this module will quickly give you a glimpse of what is traditional VLSI testing, and then we will go for the optimization techniques which will be applicable on the basic test flow. So, today's and tomorrow's lectures basically will be introduction to digital VLSI, automatic test pattern generation and design for testability. So, this part actually is a background which will be required to understand the other advanced lectures on the optimization techniques for VLSI testing. So, basically we are trying to keep the course as self-contained, so that you do not have to go back and forth with reading about the normal CAD for VLSI or VLSI testing course and then trying to look at the advanced stuff for optimization in testing. So, the first two lectures we will be trying to quickly cramp up the stuff in VLSI testing which is used for traditional, maybe with the chips which were fabricated till about early 2000s, what are the techniques and how testing was performed. So, basically as we have already discussed this, these are traditional VLSI flow that we start with basically the specification. So, we start with the specification, then we go for architectural synthesis, then we go for RTL design, then logic synthesis and then floor plan and layout. So, basically this is what is the design part and how basically for advanced systems, what are the optimization techniques, how things are getting modified or how algorithms are getting modified to handle very large scale systems has already been covered in the last 3 modules. Next part basically is the test, that is test planning. Then basically we have to plan test before the fabrication starts, and in fact whenever we talk about real test, that is we apply the test patterns and see whether all the manufactured chips are operating properly or not is actually called the manufacturing test. So, this last step basically, so in this part basically we plan what are the test patterns to be applied, how we are going to apply them, is there anything extra you need to put in the circuit to do the testing, etc. And finally after fabrication we put the actual patterns, signals and look at the outputs and see whether everything is proper or not. So, basically VLSI design and test flow, and in fact every part you will find that there should be a when you are moving from one phase to another there should be equivalence. So, basically we go for formal verification methods which we will be covering in the next module, that how formal verification can be optimized to handle large systems. So, anyway, as I told, what is testing, why it is required basically. So, basically the very well known theory we call it Murphy's law, if anything can go wrong it will. That means, if basically whatever system you make, there is a chance that it may malfunction. So, in fact testing means basically as simple as you take a system, apply some inputs and you find out whether the desired outputs are appearing at the output or it is behaving as per the specification or not. So, simple testing in case of VLSI is also the philosophy is similar, but unless a physical system, why we require testing as a special iteration or a very special part in VLSI or digital circuits or large systems is one of the very important things we should understand and which we will also look at in this preliminary lectures. For example, I take a very classical system like an electric iron. I want to test it. So, we know that it is a very traditional system, not many of the electrical irons, I am talking about the very simple iron maybe which we are using in daily life, not much of them will have faults. So, basically what you do when we purchase it, we put it in a 220 volts AC source and see that whether it is functionally proper or not, it is getting heated up or not. This is actually a testing part. Now, basically this is actually called a partial testing, because testing can be as elaborate, checking whether the steel or material which is made from which the electrical iron is made is how much it is prone to failure, how much it is brittle, all those testing can be another extreme. But basically nobody does this, because we have to test within a proper amount of time, and also it should be giving the required quality of service to the customer. Basically this is maybe done for very partially, that whether it is functional or not. Maybe you are purchasing a very cheap iron, only this amount of test will be done and it will be sold to the customer. Maybe basically if you are going to a slightly higher version, then people will also check for whether basically all the parts of the iron electrically grounded, there is no chance for electrical shocks, etc. Then you also check for the thermostat, etc. Detailed functionalities, rarely people go for that level of testing, that if there is a thermostat, you have different temperatures to silk, different type of clothes you select, whether for everything the temperature range is maintained or not. So similarly, you can find out a huge number of test parameters, like performance of power, if it claims that it is 5-star rating or 4-star rating in terms of electrical power consumption, whether it is whether it is matching to that or not. Then as I told you, that like a very stray case, you can also check mechanical parameters, like if it falls down, whether it will break, etc., etc., etc. So testing can be huge in size, but practically nobody does all those stuff, because that will neither make it logically feasible within the time limit for a product under consideration. Obviously, if it is meant for some avionics or some rocket technology, of course we will do all possible parts of the test and all extent of testing, so that nothing fails or very rare chance of failure happens. But when you are talking of an home appliance, nobody does testing on that level. So testing basically is to verify whether a subsystem is operating as per the specification, subject to time and cost benefits. So depending on this system, I will decide how much to test, so that I get it in proper time and also it is profitable. Now, if I tell, are all the electrical iron tested, or whenever you are purchasing as simple as a tube light or a bicycle or a motorbike, how much testing is done? Of course, compared to circuit, it is very few, because these are very traditional. If you compare last 200 years, the electrical iron or all the classical engineering problems are more or less similar. Slight modification has been done over the years. So what happens basically, the design part is more or less stabilized. So if you find some kind of errors which is happening in a large number of samples, you rectify the design process. So maybe one part in 1000 will have a defect, or maybe in 1 lakh maybe 2 or 3 parts will be defected. So testing is an important part, but not as important as in case of circuits. So in classical systems, testing is done, but it is actually, because more or less we know that mostly all the systems are operating fine and it has been tested over time, and not much technology changes has been there. Because if you compare a fan which is running now to a fan which is running more than say about 50 to 60 years back, more or less the technology remains same. So more or less the technology is matured, and basically not that much of deviation happens, and so testing is not of that importance as we consider as a circuit. Now what is the special issue about circuits? So you know that within last 20 to 30 years, we have come from 5 micron technology to I would say 45 nanometer technology. So when you are actually going for such sophisticated technology jumps, like we all know, the electronic gadget changes that has happened over the last 20 years is phenomenal. A person who has seen a mobile phone last 10 years or a telephone last 10 years back, he will be astonished to see a handheld gadget or a smartphone or a tab, that what is the amount of phenomenal changes that has happened in the electronic technology. So why it is possible? Because we are able to make very complicated systems like NOC and SOC on a single electronic circuit chip. How it is possible? Because we are continuously shrinking the technology from 5 nanometers, sorry, from 5 microns to 0.45 or even lower micron technology. So lower micron means whatever in the fabrication technology, whatever lines and wires you are drawing, the distance between them is started becoming shrinking. So once you start shrinking the distances, the problem happens is that a lot of failures happen. Why? Because when I am working in 5 micron technology, it takes some time for the technology to be matured and to find out what are the manufacturing defects that is happening regularly, how to change the technology for manufacturing, etc. But before such a technology matures, a new technology comes up. Like from 5 micron you go to 3 microns, then you quickly go to 1.8 microns. Why it happens? Because you have to market sophisticated and complex product to the market to get high-end products and catch hold of the market. Because nobody wants to see how a technology matures, wait and find out it's very robust. By the time some other vendor or other company will go for a lower micron technology where you can put more transistors in a chip and this system becomes more complex. So in VLSI, unlike traditional systems, huge change in technology is happening. So due to the huge change in technology, what is the problem that has happened is, before a fabrication technology matures, we quickly jump to another technology or more sophisticated or lower submicron technology, and it keeps on happening. So no technology is getting enough time to be matured so that mostly devices are fault free. So what is the profit idea? They say that I will manufacture using a newer technology so that I get sophisticated circuits, but then what? Then what will happen? You are going to have a lower yield. So lower yield means, say if you are manufacturing 100 ICs, maybe 20 to 30 will be having defects, manufacturing defects, because the technology which I am manufacturing these circuits have not yet matured. But still I have to take a risk, because otherwise some other people or other companies will use a newer technology, will give you a more sophisticated electronic gadget, and I will be left out in the market. So what I have to do? I have to manufacture circuits with a more complex technology. Of course there will be manufacturing defects, but what I will do? Testing, I have to test now all the chips, because if you are saying that a product line has 30% failure rate or 70% yield, then 30 out of 100 may have defects. So I have to test all the 100 chips, I have to throw out the 30, and the 70 I will ship into the market, make the price higher, but still I will make profit, because I will be able to have a huge market in place, and I will be able to make something which is not being sold or not being marketed by my competitors. So that is the idea of VLSI. Quote unquote, I will take a very immature technology, I will manufacture a large number of chips, test all the chips, because I know that yield may be as low as 70% or 60% even. No fabrication company basically tells what is the yield, but the number is not as high as 90% plus, it is lower. I test all the chips, throw away the faulty ones and ship the correct ones to the customers with a higher price value, but still I can give you a more complex and a sophisticated product, and I come into the market. But that does not happen in a classical technology, because in classical technology, more or less the technology has remained similar over hundreds of or tens of or 50 years or so. So technology have matured, the yield is very high, say about more than 99%. So that is why testing in VLSI is very important compared to classical system. Now if I tell you what is testing in VLSI, it is as simple as this slide. Take an AND gate, apply all the 4 patterns, and you are going to get the output. So if you are going to apply the input, get the output, you are fine. But you have to note that this is a hardware, so I have to apply it to all the chips. For example, if I had manufactured say 10,000 NAND gates, maybe out of that 100 will have some failures, because the technology to fabricate the NAND gate is not matured, but still I am using the technology, because now my NAND gate size will be very small in the nanometer technology, and I can cramp up millions of transistors and gates in one chip, so that I can give a good product to the customer. That basically is the idea. So if you see, this is very fine, I can apply all the patterns, so my job is done. But now think that this is a simple NAND gate. So if you see that the number of inputs are say only 2, so 2 to the power 4 inputs are there. So this may be the story which may be around 1970s, when small electronic circuits were made, this technology could have been applied. But again, as I told you, testing can be as simple as this, or it can be quite complicated. So one is functionality, means just they verify the inputs and outputs. Now there is something called, which is coming into the picture, is called the delay, because now chips are operating in a very fast rate. So if I apply 0 0, 1 0, the output is 1. In the next time pulse I apply 1 1, then the output is 0. What is the time taken for the output to change from 1? Because now chips are being operated at the gigahertz level. So around tens of gigs, or at least 3 or in the gigahertz paradigm, I have to be very sure that what is the time required for the output to change from 1 to 0 or 0 to 1. So in this case there is something called delay test. So along with functionality, I have to find what is the time taken for the signals to change from 0 to 1 and 1 to 0. Again, there is something called, I am not going into the details, because basically they are all parts of CAD for VLSI. I am just going to give you the idea in brief. There is something also called a fan out capability, that one gate can drive how many circuits. If you are using too many gates to drive, then what happens, basically the chips become, the gate becomes slower, and you have to put buffers. So that is also one point of test, that what is the drive capability of the gate. Now all chips actually want to work at low power because all devices are mostly handheld. So what is the power consumption of the gate? So you have to also test and find out that due to switching, static currents, or basically when the chip is not operating, there will be some drainage. So actually what is the power requirement of the NAND gate? That is also has to be tested. Similarly, there are other extreme tests like threshold level, that we know that there is something called logic 0 and logic 1, but up to what voltage level it is treating as logic 0 and beyond what level it is being treated as logic 1. Like maybe say 0 volts to 0.3 or 0.0 volts should be say treated as logic 0. Maybe if it is a 1.8 volt technology, maybe 1.5 and above should be treated as logic 1. So that test also has to be verified. Finally, extreme condition test, that if there is if the temperature is very high, the temperature is very low, whether they will be able to do all the tests on it. Now think, if you want to do it for hundreds and thousands of gates in a circuit, how much time it will require and what will be the cost? So practically nobody has been ever attempt to do all these tests for a circuit, because it will take hundreds and thousands of years to do it and it will be infeasible to do it in a practical amount of time. So basically what we do, basically we generally go for logic level test of the AND gate, and sometimes also as we will see down the line, sometimes we also go for this at speed test, because nowadays we are operating at very higher frequency, but and also power consumption to a certain level, but generally huge list of tests I have shown you basically are infeasible and impractical. Now I am not even limited to that. Now that was at the gate level, but all the AND gates basically are developed using such a transistor configuration in the CMOS logic. Now if I say that I want to actually go for the transistor level test, that can also be possible. For all the NAND gates, not only at the gate level, I want to see whether if and only if all the transistors are operating properly or not. Then you have to see the output characteristics of the transistors, transfer characteristics of the transistors, threshold voltages of the transistors. There is a huge list of tests for the transistors. So even I can do all those tests, and not only at that, this is actually the final layout of this circuit. You can even start looking at the layout from the physics point of view, that whether this line, this layout or this width of the copper implant is fine or not, whether the vias are fine or not. So even you can use a microscope, or there is something called they are probers, and basically you can even open up the chip and you can look it through a high powerful microscope and see whether all the part of the layout has been done properly or not. So basically what I mean to say is that testing in case of VLSI can be as simple as testing the functionality of a gate to as extreme as looking off the lines of the fabricated IC. So now you can understand, for a simple NAND gate it can become so complex. Now we are living in a world of system on chips and network on chips. So what will be the optimization required, and what you have to abstract, and what level you have to go. So this module will basically try to tell you that what is a practical level possible to do a test within a particular amount of time, so that it becomes profitable. If you ask me what is the golden rule, I will tell you, even if you have a cruise control IC where you have millions of NAND gates, NOR gates or gates of that order of size, you go and test all the gates at the layout level using a microscope. But the years will be infinite, nobody will be practically able to do. So we have to take a reasonable time, but at the same time, as I told you, in case of circuits the yield is not 90% plus, it is lower. You cannot keep on shipping faulty parts to the customer, so that your market will terribly go down. So I have to make a very nice optimal plane, where I have to decide that I do not supply bad chips to the customer, at the same time I do not go put too much time on testing, which will actually make it an infeasible time frame and infeasible cost paradigm. So basically what people say, what are the basic paradigms, or what do I basically require for test? So basically many people say that we require 99% plus fault coverage or guarantee. We will tell you what is about a fault coverage. I did around more than 99% guarantee that the chips will, whatever I will send you as a proper chip basically is a correct. That means out of 100 chips you manufacture, 30 may have defect, that is a yield problem. But basically when I am saying 99% accuracy, that means if I am sending some 70 chips, out of that it should be more than 99% or 99% probability that whatever I am sending as a proper chip should not have any manufacturing defect. That is what is the idea. So basically digital testing is not testing the digital circuits. It's something controversial testament basically. Digital testing is defined as testing a digital circuit to verify if that performs the specified logic operations and in proper time. Oh, that is basically the definition, because I can also tell that power, functionality, transistor level problems, all this I can add as the paradigms, but that will make it infeasible in the time frame to do a test. So people say that digital testing means you take a circuit, apply inputs at the logic level, see whether the logical functions are met, and of course the speed should be within a proper time, because nowadays we are very much concerned about the timing. So basically that is what I have to do. Power measurement, we will do it in a several different way. They do not actually put all the input patterns and check it. There is a different way of measuring power. So people think in that manner. But again, this is sometimes I can also say power, but nothing more than that also partially I can add. But mainly I am concerned about logic function and in proper time. So now I will start basically moving into the complexities, and then I will tell you what actually up to what people have done in the VLSI level, and what optimizations will be required when you are going for the ultra large scale systems. Say for example, I have a system and where I have 25 inputs. Basically it is an AND gate, 25 input AND gate. It is an AND gate with 25 inputs. Now how will you test it? Of course you have to apply all zeros to all ones. All the patterns you have to apply and see whether the output is proper or not. So basically in all cases the output will be 0, except in the case with all 1, the output should be 1. Very simple way of this is actually called automatic test pattern generation, ATPG. Or test pattern generation is not automatic because I am doing it manually. So all possible patterns you have to apply and your job is done. But now what is the number of patterns? The number of patterns even for such a circuit is 2 to the power 25. So if you are, that is you need to apply 2 to the power 25 patterns. If so much huge number of patterns are applied per second using a megahertz tester, it requires 33 seconds per chip. Now as I told you, in case of circuits, all the chips has to be tested. It is not a software, it is a hardware. So, and also the yield is not very high. So, all the chips you have to apply so many number of patterns, and you have to see whether the chip is operating properly or not. If it is proper, you ship it, otherwise you throw it in the dustbin. But now basically if you are wanting to apply 2 to the power 24 patterns, it is going to take a huge, extremely huge number of infeasible number of years to do the testing. So therefore this is actually called functional testing, in which case you apply the patterns, you know the functionality of the circuit and see whether the functionality matches. So this functional testing cannot be performed due to the extremely high test time. So one key optimization that was done even in the case of VLSI era, because in this lecture when I will be talking about VLSI, you can think about basically up to processor level or slightly lower scale circuits, but when I will be talking about SOC and NOC, you can think about the high scale computing platforms, which is the main emphasis of the course. So functional testing was at all not even possible for the VLSI part. So just after low scale integration, people have thrown it out. Now there is something actually called structural testing. So what is the structural testing? In case of structural testing, I will not be concerned much about the whole functionality of the circuit. I will basically look at the structure and I have to find out whether everything is proper or not. So basically structural testing was introduced by the gentleman. So it says verify the correctness and the specific structure of the circuit in terms of gates and interconnects. So basically what is the idea? I will not look at the entire circuit as a functionality. So it may be a processor, it may be a calculator, or it may be some kind of GCD calculator, it can be something like comparator. So for my idea is that I want to see whether all the gates, which are the basic building blocks of the circuits, and interconnects, whether they are properly functional or not. I will not see and I will expect that if all the gates and interconnects are proper, then I will expect that the whole circuit should operate fine. Of course, but anyway in this case we are not verifying that even if all the gates and the circuit lines are proper, still there can be some functional problems, but that is a very rare case. So what idea is that they say that all the gates and the wires are individually tested, and interface we are not much bothered about whether the interfacing is happening properly or not. All the components like gates and interconnect lines are tested and we are integrating it, and then we are expecting that everything should operate fine. And truly speaking, statistically it has been found out over last 20 to 30 years that more or less this is a very good strategy, because anyway functional testing is out of scope. And you will find that structural testing takes very less amount of time compared to functional test. Structural testing is a much faster process of doing it, but only what I compromise here is that I do not actually test the basic the interface and overall functionality. So basically structural testing is the kind of functional testing at the unit level, that is only at the gate and the interconnect level. Whole level I am not going to do. So one key point I am going to tell, or thumb rule, whenever we are going for optimization in CAD for VLSI, they are optimization at the level of the algorithms or time. to generate the circuit or do the testing. So when we will be compromising? We will be compromising mainly at the quality of the, basically little bit compromising, obviously you cannot compromise much. So compromise will be the quality of test, quality of design, optimization or the area and power requirement of the circuit. That is, the quality of service expected will be slightly compromised, but the algorithms will be very fast so that you can get the output in a reasonable amount of time. So optimization is not in the performance of the circuit. So this you can take this as a thumb rule kind of a thing, not a very regular rule, but mostly thumb rule. When you are talking about optimization, it is mainly at the CAD part of it or the algorithms to design the circuit or test part of it. So that even if it is a very big system, I can do my job very quickly. So that, but there will be very minimal quality compromise in the device or the circuit. Like when I am going from structural testing to functional testing, I am not testing the functionality, and also now I am not very explicitly or rigorously testing the interface. I will take an example. So maybe this is my circuit, there is 25 inputs and 1 output. So last case what I have done, I have given 2 to the power 25 inputs and I have done the functional test. So once the chip is functionally tested, I am very happy that everything will be properly done. But now what is structural testing? Because anyway I cannot apply that pattern. So what I will do here is, I will test all this, I will test all the individual gates at point of time. So all the gates have how many inputs? They have 5 inputs. So 2 to the power 5, that is equal to 32 inputs will be applied to the gates, all zeros to all ones, and the AND gate. So basically only for the all ones the output will be 1 and so forth. So I will test all the individual gates at the level. So 32 into 6, there will be some 100 patterns will be required compared to 2 to the power 5. 2 to the power from 2 to the power 25, I have come to the value of 32 into 6. So huge jump is going to happen, because this is something like divide and conquer policy. So unless from 2 to the power 25, you are actually breaking up into 6 into 2 to the power 5. So that way. But again, I am just going to check the gates and I will check the interconnects. But now if I interface everything, I am not going to test that part. But the gain I am achieving is from 2 to the power 25, which is infeasible to 32 into 6 patterns. So that is what is an optimization for the test time, but slight compromise in the quality, because statistically it has been found out that even if all the gates or interconnects are separately operating fine, interfacing circuits are, when even the circuit is interfaced together, the circuit operates also in a very proper fashion. So this is what is given. So from this is basically 160 inputs are required, which is much less than 2 to the power 25, and you just require such a less amount of time to test a circuit. So very easily you can test hundreds and thousands of circuits using this structural test. Now what are the penalties? Each individual gate is tested, but integration is not tested. So actually another very important thing is that which I will show you a figure and it will be clear, that these 2 points, that I am telling, of course you are going to test these circuits. So but this is a chip, this is a black box. You have seen that all the VLSI chips, so there is a plastic cover and after that there are some pins which are coming out. But if I am applying the inputs at this, I need to see what is the output of this pin. But again this pin is inside a circuit. So how I will observe this pin? Similarly, this is observed very good, but if I want to apply some inputs to the gates, I have to apply these inputs directly over here. Because if I try to control these inputs via these AND gates, again the problem will blow up. So I need a direct access to the line for read and write basically. But how I do it? Because this is a black box. So that is one very big problem of structural test. That is, to test individual gates, controlling and observability is very much required. Because it is a circuit, only the input and output pins are there, but how do you probe the internal speed? So there are millions of internal lines in a circuit. What you can do? You bring out everything. It's an impossible, it's a another more impossible solution, because your chip will have some hundreds and thousands of pinouts, which is not possible. Nowadays with a very complex processor also, the number of input output pins are maybe 1024 or even lower than that. That actually is also a ball grid array package. So this requirement is infeasible. So how to do that? So this is basically a picture and how to do that, even if you are having a pinout. So if you can see, they have put some multiplexing arrangement and these are the pinouts they have brought. In fact, again also this also you have to, basically I am just going to just give you the gist, because you can easily find that in any test book. So this is actually a multiplexer. So what happens basically, so whenever you want to apply something directly to this gate, you will actually cut this out to this multiplexer and directly give the input from the outside. Similarly, so you have to again give some input to this gate also, then I have to actually cut this out, and I am having a multiplexer which is having 2 modes, one is called the normal mode and the test mode. The test mode basically the input to this from G5 to G6 is cut, and there is an external pin which will directly give input to this, right. And then basically this actually solves the problem of directly applying something to G6. But when I will be operating in the normal mode, you make the test mode equal to 0. So, the test mode equal to 1. So, in this case the external lines will be cut and the output of this gate will be fed to this gate and your job is done. That is, you can apply some patterns directly to these inputs. Again, as I have already told you that I have to also explicitly observe these lines when I have to test these two gates. But how do you again observe? Again you can change the configuration mode, the output from this can be observed to this line. So, by actually having some multiplexing arrangements, we can also go for observation of the internal lines, because as I told you, you cannot bring probing out, you cannot have infinite number of probings and control. But still you can see I require many probe outs, that is I have an extra pin for this, 2 lines I have to observe, so I have to bring 2 extra lines of the chip and again 2 lines for the inputs of this gate. So, basically 2 lines means there are other 5 gates which I have not shown, basically in fact there will be 5 lines which will be have to take as outputs, there will be again 5 inputs for this control pin which will be again taking as the output. So, some extra, that is in the gist of is that you can go for structural testing, but the problem here is that you can very easily go for structural testing because the number is less, everything is very feasible, but I have to sometimes observe these lines directly and sometimes I have to also control this line directly to test these gates at the individual level. How to do this? You have to actually make some pinouts for all these parts and also you have to have some multiplexing arrangement so that I can apply directly something to this. So, you can understand a huge number of extra multiplexers will be required and huge number of pinouts has to be made corresponding to all the points which are internal to the circuit chip which you have to observe and control. So, structural testing is a good idea, but I cannot make out so many number of pins. So, now how to solve this problem? There is something then came up which is called a fault model. So, this was a very interesting discovery, but if you ask me that how it is mathematically correlated, it is very difficult to answer at this point of time. But it is statistically found out that it is a very successful model. So, what do you mean by statistical testing? Very simply, let me tell you that initially we told that how do you do a test? That you go for functional testing. Then you say that functional testing is very difficult to the power n complexity, etc. Then what we do? We go for structural testing. But in structural testing only you are testing the gates and mainly the interconnects. Then if I integrate, how do you guarantee that the functionality is proper? It is found statistically that if you go for functional testing, if you go for structural testing, then for 99.9% plus accuracy you can predict that the structural test is, if the structural test is proper, the functional test is also proper. So, with that correlation from statistical finding of testing of physical chips in the lab, we have found out that structural testing takes lower time. At the same time, the correlation is very, very nice with the functional test. So, that is how it happens. But again, the structural testing is having a big problem. What is the problem we have seen? The problem is that you have to bring lot of pinouts to see the internal pins of the circuit and also control the internal lines of the circuit. That is a big problem that is happening. Then something came with something called a fault model. So, what is the fault model? In fault model they say that we are not even concerned with the functionality of the gates even. First we were not concerned with this, first we were concerned with the functionality of the circuit. Then we went to structural testing where we are not concerned about the functionality of the circuits, rather we are concerned only about the functionality of the gates. But now in the third level, which in fact the de facto standard which is now used everywhere, is the fault model. In this case we are not even concerned about the functionality of the gates even. Rather what we do, we say that there is a fault model. So, what is a fault model? Fault model means they assume that there will be certain kind of faults in the circuits which by statistics they have found out is the most likely to be occurring, and then you have to verify that those faults are not there. So, we are not even concerned about functionality of the gates, but what we assume that there can be certain faults which are very predominant and you have to verify that those faults are not there. If those faults are not there, we will assume that the circuit is operating finally proper or not. Again, this is an optimization to save time, but slight compromise in the quality of test. But again, as I told you, by statistics people have found out that if you are having a proper fault model, the accuracy with functional testing is 99.9 plus. So again reiterating, optimization is all happening in the terms of test time, test pattern generation, algorithms, etc., but slightly compromise with the quality of test. So all the optimizations are in the terms of algorithms. So again, one very simple fault model is called an open fault model. That means whatever lines you have fabricated, that line may be basically open because of some kind of less amount of doping or some kind of issues with the fabrication technology, some lines will be open. So this is a open fault. So what you have to verify? That none of the lines are basically open. So what you can do? Simply you can apply all 1, 1, 1, 1, 1 and you have to get a 1 over here. Of course, if you apply all 1s and you get a 1 over here, no line is open. But in fact, you see I am not even verifying the functionality of the AND gate. So what I am just verifying that no line is open, because if the line would have been open, this would have been 0 and I would get the value 0. I would say that there is some open faults in the circuit, as simple as that. So basically open is also called stuck at 0 and I will come to that what is the name of the fault model. So this is a fault model. So people will say that these are some tentative faults, this has to be tested and don't even bother the functionality of the gates. So now in the previous case for the 5 inputs gate we had to apply 2 to the power 5 inputs. But now in this case I will only apply maybe 5 inputs. From 2 to the power 25 I have come to 2 to the power 5, now I am coming to 5. So what are the 5 or in fact you can call 6. They will assume that all these lines may have stuck open faults, that is the lines are cut. So you have to just apply 5 patterns. If in fact I am sorry, you have to just apply one pattern. If there is 1 1 1 1 1 and the output is 1, then it can be verified that none of the lines is stuck open, that none of the line is cut. So you are fine. So in fact from 2 to the power 25 I am coming to 2 to the power 5 and in fact I am coming to one pattern. One pattern actually tests all the stuck open faults. In fact, I mean you assume that I am applying 1 1 1 1 5 times, but it is actually not required. I am applying in, means mathematically speaking, all the ones have been applied for each individual faults, like this can be open, this can be open, this can be open, this can be open and so forth. But in fact technically only all ones if you apply, you can verify that none of the line is stuck open. Then your job is done. So with one pattern I can verify that there is no stuck open faults. Now from 2 to the power 25 I have come to a single pattern to do the test. Huge save in, what do I say? Huge save in the number of test patterns and time. But where I am losing, I am not now even testing the quality of, that is the functionality of the circuit. I am also not testing the functionality of the gate signal. Just I am finding out that there is no stuck open fault. Because somebody told me from statistics findings that such type of circuits mainly are having stuck open faults. Just to verify there is no stuck open faults, then you can easily sieve the chips in the circuit and the accuracy is 99.9% plus correlation with the functional test. So on that belief only I am doing it. So this is actually called fault model. So now what are the basic type of fault models which are in practice? In fact this whatever I have said is this stuck open is just very stray example, but there are some real life fault models which people have found out statistically and now are being applied are this one. So that is the stuck at fault model, which is very popular. So it says that none of the lines should be stuck at 0 or stuck at 1. That is means no line should be permanently 0, no line should be permanently 1. In fact whatever logic I am giving to a line, it should be ported to the other part of the circuit. And it was found statistically till last 10 years or 15 years that if a circuit do not have stuck at faults, the circuit is 99% probable to be working as per the functional specification. So that much guarantee was given. So stuck at fault model was a very powerful fault model, and in fact even it is also the de facto standard that everybody starts with the stuck at faults. Then there is something called a single stuck at fault model, which was the most popular one. That is at a time you assume that only one line is having a fault. First you test this line is stuck at fault or not, then you go for another line and so forth. You assume that at a time only one line will be stuck at fault or not. Then there is something called multiple stuck at fault model, because in that case any 1, 2, 3 any number of lines can have stuck at fault. So you have to take all individual lines, then you have to take pairs and then take 3 lines and then quads and so forth. This is slightly complex model, nobody even actually applied this. People had found surprisingly it is a boon that if you verify that there is no structural stuck at faults in the circuit, 99.9% probable that it is functionally proper. Because multiple stuck at faults also the fault numbers are high. Then as I told you, nowadays we are also operating at higher levels of speed. So there is something called delay fault model, that you have to find out whether the input output the delay is maintained, and there is something also called a bridging fault model. The bridging fault model is that you have to verify that no 2 lines are getting shorted. So more or less these fault models are still used even in very advanced circuits. So stuck at fault model was applied in the traditional level. Nowadays delay faults and bridging faults are also being incorporated. So what they verify that no line should have a stuck at 0 or stuck at 1. Similarly the delay you measure that if I am giving 1 or 0, the output and input should take place within a given amount of time, and also have to verify that no 2 lines are stuck. And one important point I want to emphasize, people go for single stuck at model or fault model. So what is a single stuck at fault model? Single stuck at fault model means at a time you assume that only one fault is there. It is tested not to be there, then you go for the next fault and so forth. Like in this case I will see if there are 10 lines, first I will see that first line is stuck at 0 or not, Then I will go for the second line and third line. I will not consider pairs and triplets in this case because the numbers will be very high. Similarly, for the bridging fault, generally we take 2 lines at a time, and some modern cases they take 3 lines at a time which are in close proximity, and then you take all pairs and you see whether there is a bridging fault or not. That means you take if there are 3 lines say, so I will take 1, 2, then I will take all the combinations I will take, and whether I will see whether one at a time. Say for example, if I have say for example 4 lines, 1, 2, 3, 4 say, so basically I will see whether these 2 lines are stuck at bridging fault or not, but I will not check simultaneously that whether I will not try to simultaneously assume that these 2 bridging faults are there. Single stacked fault model means first I will see whether this is there or not. If I verify this is not there, then I will go for this, then maybe I will basically take the other combinations, like maybe after that I will take this combination and so forth. I will drop this and this combination because they are quite far and short probability will be very less. So, this is how basically it goes. So, what is the idea of fault model? Basically, you do not even test the functionality of the gate, just verify the faults which are given in a list are not present in a circuit. If you are able to do that, then your testing is done. This is a way, this was actually a path breaking optimization in the area of test. So, whenever we moved from low scale integration to and from medium scale integration to high level integration, that is VLSI, we all moved to fault models. Nobody could do functional or structural test at that level because of the complexity. So, fault model was a phenomenal discovery that statistically it is shown that if you verify on basis of a fault model, mainly the stacked fault model, very high probability that 99.9% that the circuit does not have any functional defects. But there was a slightly some people have modified the fault model for a fan out. I am just showing you the stacked fault model. So, for a circuit like this, they are actually have to point out all the nets of the circuit, and you have to verify that none of these lines have stacked 0 or stacked 1 fault at a time. For example, if I want to test this, first we will assume there is a stacked 1 fault here and apply certain inputs and see that the stacked fault is not there. Then you will erase it and take stacked 0 fault. Then you will apply an input pattern and see that the stacked 0 fault is not there. You will reiterate for all the lines of the circuit and then your testing is done. So, in this case there is 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 9 lines are there. So, 9 into 2 will be equal to 18. So, 18 faults will be there. So, you have to at max apply 18 test patterns. But actually it is shown in theory and with examples it can be, as I will show you, that you will not even require 18 patterns. For one pattern more than multiple number of faults get detected. So, maybe only 3 or 4 patterns will be required to test it. So, one byproduct that has been found out for test at fault model is that if there are say 10 faults, if there are n lines, of course there are 2 n faults, 2 into n, because stacked 0 and stacked 1. But 2n number of patterns are not required. The patterns are much lower than that because one fault pattern can test multiple faults basically. So, in this case we will not require 18, we will require much less than that. But one important point I just want to emphasize, that this is a fan out branch. From here I am going to all these parts, 3 lines I am going, but I do not consider this as a electrically even line, same line. What I do is that I have I can have faults here, I can have faults here as well as I can have fault here. So, this is a fault model. So, the fault model assumes that the fan out branches are independent. If when I will consider a stacked 0 fault here, I will assume this line to be fault free. But when I will be having a when I will be having a stacked 0 fault here, of course this whole line will be affected. But when I am having a stacked fault at this zone, at this line, so this line will be only affected and the other branch of the fan out will be fault free. So, this is basically the stacked fault model, which is the de facto standard and was applied till a very long time. So, in this preliminary lecture I will be mainly covering the stacked faults, and then when I will be going for the advanced lectures, maybe we will try to see something about bridging faults and delay faults, that we will try to give you a coverage. So, as I told you, so if you have, then what is the question of single stacked and multiple stacked faults? So, single stacked fault means, as I told you, if there are n lines, the 2n number of faults can be there, stacked 0 and stacked 1. But why people have not considered multiple stacked faults? Because if there are n lines and you want to consider multiple stacked faults, then the line can be either stacked 0 or stacked 1 and fault free. So, 3 to the power n minus number 1 minus 1 is for all normal case, can be having a fault. So, 2 lines, 3 lines, 4 lines, all possible combinations if you want to take, the number is very high. And people have found out that it will take more time to go for multiple stacked faults, but the accuracy is only slightly improved considering a single stacked fault. So by statistically, people have found out that single stacked fault is manageable in number, provides acceptable quality of solution, and that is why it is the most acceptable fault model. That people has found out by real experimentation. So that is basically de facto standard. Now again I am going to take the same circuit for example, and I assume that there is a stacked 0 fault at this line. Basically that is the idea. Then what I have to do, in this case there are 25 lines, so it is 25 plus 5 internal lines, there is 5 plus 1, that is 25, 30, 31. So there are 31 lines here. So worst case there will be 62 number of faults, and 62 number of patterns may be in the worst case required to test it. But again, what are the benefits I will show you, that you do not require any number of pinouts from the internal branches. That is how is the most gain of the stacked fault model or any fault model, that I do not require to probe it, neither I require to send anything as an input. I will just use the input and output lines to do the testing. That is what will be the most amount of gain compared to simple structural testing. But along with that, you will be very happy to see that one pattern will detect multiple stacked faults. So even I do not require 62 number of test patterns, that number of patterns will be very, very low. So let us assume that this line is having a stacked 0. I have to verify that none of the line has stacked 0, and also have to verify that none of the line has stacked 1. So stacked 0 here, say I apply the pattern all once. So what is the case? The output will be a 1, correct? So now if this line is stacked 0, so what I am going to get the answer? I am going to get the answer as 0. So by applying all ones, I can verify that this line does not have a stacked 0. Similarly, it is very easy to observe that all ones and the output is also a 1, basically guarantees that none of these lines has a stacked 0. So all 1 pattern basically verifies these 25 lines plus 5, 30 and 31 lines. These all 1 patterns basically verifies 31 stacked 1 faults is not present. So one pattern, that is all ones, verifies that none of the line is having a stacked 0. That is one pattern, 31 faults gone. So that is the beauty of structural testing. And also if you see, I do not have to probe anything in between. What I am doing is I am applying the inputs and just I am looking at the output, and my 31 faults are gone, or means covered. That is actually called fault coverage. All ones I am able to test 31 faults. Again, as I told you, you have to verify also that none of the line has stacked 0. So I am using a stacked, assuming that this was a stacked 0 fault. Now I am assuming a stacked 1 fault over here. So now what is the pattern? So of course I am applying a 0. It is very obvious that if the line has a stacked 0 fault, you have to apply a 1 at this line and vice versa. So it is a stacked 1, so I am applying a 0 over here, and all lines I have to keep it 1 to keep the controllability of the AND gate. So if the circuit is normal, I will get a value of 0, because I am applying a 0 at the input. But if this line is stacked 1, then what is going to happen? You are going to get the answer as 1. So if the answer is 1, you know that this line is having a stacked 1 fault, else the circuit is normal. So this pattern actually tests stacked 1 over here, and also you can easily verify that it will also test a stacked 1 over here, because even if this line is not stacked 1, but this line is stacked 1, you can have a fault like this, and of course this line is stacked 1, you are going to get it. So one pattern in this case is testing 3 faults. Again, if I assume that, say, this line is having a stacked 0, this line is having a stacked 0, then what I have to do? I have to apply 1, 1, 1, 1, 1, 1. Sorry, I am saying about stacked 1. So if I assume that another line is stacked 1, so you have to apply all ones in all the inputs excepting for this line, and the same philosophy will follow. So how many patterns will be required? As you can see, you will be requiring 25 patterns, because each pattern will verify the input line does not have a stacked 1 fault. So and along with each pattern, not only test the input faults, but also will test this fault as I have shown you, and also the stacked 1 fault at the output. So 25 plus 1. So 26 patterns are actually solving the problem for you. And you have to understand that we do not at all require to have any probing inside the chip. That is what is the foremost advantage of stacked fault model. Structural fault testing was very good, but the problem is that we have to actually probe out the values. So now what we have got from 2 to the power 25, so we have got into 2 to the power 5 into 6, still this is okay, but structural testing means you have to do lot of probing, not at all feasible. Then we have come to a technology which is called test with a fault model, where you are only using 26 patterns to test the faults, because here I have shown you all ones will verify that none of the nets has a stacked 0 fault, and then with the test patterns of working zeros like 0, 1, 1, 1, 1, then 1, 0, 0, 0, sorry, means there is a series of working zeros like 0, 1, 1, 1, 1, then 1, 0, 1 0 1 1 1 1 dot dot dot, finally again 1 1 1 1 0. So if you apply these 25 patterns, all these stacked 1 faults will be covered. It is very obvious. In the last case, one pattern was covering 25 or one pattern was covering 25, 30 plus 31 faults, but in this case actually the number of faults covered per pattern is, for the stacked one is less, it is only covering 3 patterns, 3 faults, one pattern is covering 3 faults. But anyway, so this shows that structural testing actually brings down the number of test patterns to a huge level. Not only that, it also basically has no requirement of any probing in the circuit. So this is actually called structural testing with fault model. So in case of all VLSI circuits, even with the recent ones, people have the basic fault model as the, people do testing on the basis of a fault model, because nobody can go beyond this, because that is an optimized level in terms of test time. But again, as I told you, what is the compromise? The compromise is you are not testing the functionality of even the gates, but statistically found the correlation is very good with functional test. So this is, I have just given you the picture. So one fault model, one pattern. So all the good things about the structural and fault model is test over here. So pros, no DFT circuit, DFT being designed for test circuit like multiplexers, which are additionally you have to put in the circuits. Low test time, because one test pattern is covering multiple faults. The only disadvantage is that functionality is not tested even for the gates and flops. But history says that there is a huge correlation, so not much is compromised. But the optimization is at the level of algorithms or techniques to do test faster, but slight compromise is on the quality of test. Now, so this was a simple circuit. So I have obtained these state patterns manually. Now the question comes, if you have a complex circuit, how do you generate the test patterns? Of course, given a circuit, I cannot do it manually. So this is actually called automatic test pattern generation or ATPG algorithms, which is the heart of test. So given a circuit and a fault model, you have to find out what is the minimum number of test patterns required to do the testing. So in VLSI era, our target of coverage was 100%. But given a fault model, you have to cover all faults. That is what was the de facto standard. So whatever you do, you try to receive 100% of coverage. So you require some hundreds of test patterns, because I have shown you that it is not very high. For the 25 input circuit, you require only around say 26 circuits to 26 patterns to do it. So even for a large processor also, the number of test patterns by this technology was not very high. But now when you are going to NOC and SOC era, the circuit itself are becoming so large and so complex that even in this level of abstraction or optimization, that you are not even testing the functionality of the circuits, of the gates and nets, we are just going for a fault model like a stacked fault model. Still the circuits are so large that even 2 into n is so large, or the number of faults even in a by the stacked fault model is so large in an NOC and SOC systems that still these things will not be that much applicable. So when we be looking at optimization of ATPG from the context of SOC and NOC or very large scale circuits, we will discuss all those paradigms. Now basically we are looking at how basically automatic test pattern generation actually has served say over the typical medium scale or certain large scale circuits, not to the level of systems. So one was actually called the fault simulation. So it's a very simple idea which I have already done, but we will have to develop software codes to do automate it. So you take a normal circuit, then you take circuits with fault 1, 2, 3, 4 and so forth. Fault means the stacked fault. So if there are n nets, in the worst case you will have 2n such circuits. Then you take a random pattern. You can assume that all ones is a random pattern, some random pattern you take. Then you simulate this normal circuit with all ones and all the faulty circuits with all ones. Then you will find out that there is a mismatch in the result. Say maybe normal circuit, fault 1, fault 2 up to fault, all there is a mismatch. That means this one pattern is actually covering all the faults, because if you apply once, all ones, the normal circuit and the faulty circuit will have a difference. But say for example with this one, only circuit with fault 1 and fault n are different in results correspond to the normal circuit. That means these all one patterns actually can differentiate fault 1 and fault 2 corresponding to the normal circuit. Like for example, if it is an AND gate and you are having a stacked 0 fault, then if I apply 0 0 over here, then the output line is having stacked 0. So of course with this input of 0 0, both the normal AND gate and the AND gate with stacked 0 fault at the output have similar outputs. So that means this fault pattern is not able to cover this fault. But if I apply 1 1, in the normal case the answer will be 1 and the faulty gate answer will be 0. So we say that the pattern 1 1 detects this fault or covers this fault. So what I do, I take some random patterns and I apply to all the circuits, normal circuit and the failure circuit. Wherever there is a response mismatch, that means that pattern covers that fault and we eliminate it. Then again we will say another random pattern will generate, say 1 1 0 1, then again I will repeat it. Maybe then I find that circuit with fault 2 has a mismatch. I will keep on doing it till all the faults get detected, but in fact that does not happen. We start with a random pattern set, then we find that the coverage goes like a curve like this. Say maybe after appearing about say 100 patterns, typical number I am saying, you will find out that till about say 60 or 70 patterns, new patterns you are applying, more number of faults are getting detected. But after that this curve will saturate. That means now what happens, even if you are applying newer patterns, some of the faults are not going to get tested. That means they are called difficult to test faults. Some faults are called easy to test faults, where what happens basically you take some random pattern, then apply it and you will find out that the faults are getting detected. Mainly such faults are stuck faults at the input lines or the output lines of the circuit. But some faults will be quite difficult, which will be say in the middle part of the circuit, etc. In such cases, if you are applying random patterns, you have to apply a huge number of random patterns and only a very few of them will be able to detect those faults. So we call it difficult to test fault. So idea is that first we go for fault simulation based automatic test pattern generation. You take all the faults, apply some random patterns, maybe hundreds of them, and then see which faults get detected. Whichever fault will remain, we do not then go for basically random testing. In that case, it will take longer time to do it. We mark them as difficult to test faults, and then basically we go for path sensitized based ATPG. That is actually called deterministic ATPG. That means we will take a particular fault, sensitize it, propagate the value to the output, and do a line justification. I will tell you with an example in this case. In fact, the idea is that now it is not a random test. Basically what we are doing, we are applying, taking a fault, and deterministically we will find out what pattern will test it. Because say out of say there were 30 faults, I applied 20 test patterns randomly and say out of 30, 28 faults get detected, 2 faults remain. To detect these 2 faults, maybe I have to apply some another 30 random patterns to find whether when the fault will be detected, because they are difficult to test faults and they will be maybe detected by only a single test pattern, and that pattern has to come in random fashion. So the probability is less. But easier fault means they will be covered by multiple number of faults, multiple number of patterns. Say as I told you, if you take an AND gate and if you have a stack at 1 fault over here, then you can detect it by 0 0 input, 0 1 input, and 1 0 as an input. All this will detect the stack at 1 fault at the output of AND gate. So it may be called as an easy to test fault. But if you are taking say I have a stack at 0 fault at the output, then you have to apply only the pattern 1 1 to differentiate it from the normal circuit. So in that case I can tell that the stack at 0 fault at the output of the AND gate is a difficult to test fault. So if a fault has multiple test patterns, then if you are going for a random test, it is highly probable that any one of these patterns will appear from the random set and the fault will be detected. But if it's a difficult to test fault, have a very limited test pattern, then probability of those appearing will be lower. So basically that we have to go for a fault sensitization, propagation and justification based approach, in which case you will particularly target that fault and test it. So I will come back to this slide later on, but I will just give you an example. The slide, there is a 5 value algebra basically. In Boolean circuits you have 2 value algebra, but when you are going for test we go for 5 value algebra, not much change. One is a D and one is a D prime. So D actually means basically under normal case the line is 1 and the faulty case the line is 0, and D prime means just the reverse. Under normal case the circuit is 0, the faulty case the line is 1. Because now as we have fault, so we are extending the 2 valued algebra to a 5 value algebra, just this nomenclature. So just keep it in mind. This is what is shown, that maybe if the output is having a stack at 0 over here, then if I apply a 1 1, the normal case the answer will be a 1 and the faulty case the answer will be a 0. That is the output of the AND gate. So that is, we will mark this as D. Similarly, if we are applying 0 0 and the line is stuck at 1, so the normal case the answer is 0, the faulty case 1, the answer is a D prime. So you can just look at this slide this thing. So maybe if you have a AND gate, one input is 0, a stack at 1 fault is there, another input is X. X means I do not know what I have applied, so in that case the output is X, because we know that in AND gate this is a controlling pattern, so the output will be X. This is the Roth's 5 value algebra. Now I am going to take you through an example of path sensitization based ATPG, that is not a random ATPG, which is a deterministic ATPG. So let me zoom it. Yeah. So let this be a circuit. Now for example, just see that this is a B is a line stuck at 1 fault. I assume that this is a difficult to test fault. Just assume that this is a difficult to test fault. That means I applying random patterns, you could not test it. So what you are going to do? So what do you mean by sensitization? This is a very logical idea that if this line is stuck at 0, how will you test it? You have to apply a 1 over there. Obvious, if you want to test that whether a bulb is fused or not, so what you will do, you will put the light on. So if the light glows, the bulb is okay, or otherwise the bulb is fused. So similar logic here, stuck at 0 means I have to apply just one pattern here. Now I have to find out, because as I told you that, basically there is no extra pinouts. So only A, B, C and D are the inputs and H is the output. So only way is that you can apply some patterns over here and you can see the pattern at the output of this. This is the only thing you can do, nothing extra than this. So I have to actually bring out the affect. So what is the affect over here? Normal case 1, failure case 0. That is actually D. So the D should appear here and here. But what I am trying to do, that is I have to propagate the value to the output. That is, the affect is D. So the D has to be brought to output. So there are two paths. Either I can bring the affect from here or I can bring the affect through this path. These are the two paths. That is E, F, G, H is one path, I, J, G, H is another path. Some path you have to select and you can bring out the output to that path. That is actually called propagation. Then after doing that, you have to also justify that whether it is possible by logical signals. That there should not be any clash. So in this case, I am taking a 1. So in this case, I will get a D, because in this case it is actually normal case 1, failure case 0. So it is D. Somehow I am selecting this path as the propagation path. So D will be there, D will be there. There is an inversion, so it will be D bar. So basically I should get a normal case 0 and a faulty case 1 in this case. So if I apply, if I sensitize this, I have to sensitize stuck at 0, I sensitize by 1, the output value I have propagated. So if the output is 0, then the circuit is normal. If the output is 1, I know that there is a stuck at. This is going to happen. So I have selected this path. Now what I have to do, I have to actually justify. So what do you mean by justify? That means I should be able to derive this signal. So this is an AND gate. We all know that AND and NAND gate means to propagate the value to the output, is a controlling input value is 1. Because if I make this line 0, the output will be default 1. So the fault affect propagation will be lost and you are not going to add any difference. If I put 1 here, it will be, the answer will be 0 and a if I put a 0 over here, which is the controlling value, the answer will be a 1/1 at the output. Then actually nothing you can observe. For both normal and fault case, the value will have similarity. So what I have to do, I have to have a controlling value I have to give. So actually I will put a 1 over here, so that the D gets propagated here as the D bar. So this one will have value over here, so this one D will be settled at 1. So this is actually what I am calling a justification. Sensitization, propagation to the value to the output, now I am saying whether it is possible to do it. Similarly, this is the OR gate. So if it is the OR gate, what I have to do, you know that the controlling value is 0. If I put a 1 over here, the output of the OR gate will become a 1. So in that case, the fault propagation will be lost. So I have to put a 0 over here. So if I put a 0 over here, of course, you require to have a 0 over here, I should have a 1 over here as well as I require a 1 over here. That is what is the requirement. To have a 0 over here, I should have a 1 over here, 1 over here. So 1 and 1 basically is 1 in AND gate and NAND gate it is 0. So I require a 1 over here, but if you see, there is a conflict coming over picture. So what is the conflict? That I require a 1 over here, so that I get a 0 over here and so forth, and C also has to be made 1. But this line is having a fault, I am putting a B is equal to 1, so this is D and this is D. So there is a conflict. So what I want to show here is that automatic test pattern generation also not very simple, that you have to try multiple iterations to find out which is an exact test pattern, and if it is a big circuit, you have to apply an algorithm to do that. So there was a problem over here. So I cannot justify. I could sensitize, I could propagate, but I could not justify. So what is the option? There was another path here where I could have propagated the fault effect. Now I will try that. So let me quickly zoom it and show you. So in this case, this was D. So this is simple, that because there is only one way to sensitize it. Stack 0 means you have to apply a 1. So is 1 means normal case 1, faulty case 0. Now I am taking this path for propagation. So this path is propagation means D will be inverted, D bar, OR gate D bar, and again a second inversion is D. So in this case what is going to happen? Normal case the answer is 0, the faulty case the output will be 1. So sensitization is done, propagation is done. Now I have to justify. So again this justification is simple. Anyway this is D, so I have to have a 1. Now if you see, this line is D bar, so this line has to be a 0. Of course, because otherwise the controlling value will be lost. Now how do I get a 0 at the output? A also equal to 0. Now you are done. So in this case, by selecting another alternative path, basically you could find out a test pattern, because fault sensitization, propagation and justification are all satisfied. So what is sensitization? take a line which is a fault, apply the signal which is opposite to it. Propagation means you have to sensitize this is sensitization, that is D, you have to propagate it to some output pin of the circuit, and justification means you have to track back and settle out the primary inputs. So all three could be done with this new path. So that is what I am saying, automatic test pattern generation is not very simple. That is why we first go for random test and then we go for this automatic test pattern generation based on algorithm targeting each fault at a time. That is sensitize, propagate and justify approach we do, but we want to do it for a very limited number of faults. But again, if you take a very large circuit like NOC and SOC, you can find out that this number of difficult to test faults also will not be less. It will also be very high. If the system is large, where inside they will be embedded, and basically you find out that in one trial you may not get a pattern. You have to reiterate and find out. If the circuit is small, this is a very good standard to follow. Small in the sense that I am not talking about the NOC, SOC, even for a quite simple level processor also this is well applicable, but if you are going for NOC and SOC level, this will take an enormous amount of time even for such large systems. But this technology was well accepted in the till about say circuits at the level of processors, MIPS processor, slightly at the level of medium scale and slightly towards the slightly higher scale it was possible. But with system of chips, NOC and SOC, even this paradigm is not going to work, it is going to take enormous amount of time. So when you will be studying optimization, we will see how to handle this with higher level fault model and higher level of test, that you are going to see. But anyway, let us come back to the basics which you are trying. So basically now what happens, A equal to 0, B equal to 1, C equal to 1 and D equal to 1. So this becomes your test pattern to detect this fault, and the output is D, that if the circuit is normal, that means this stacked 0 fault is not there, you are going to get the answer 1. If you get the answer 0, then you know that this stacked fault is there. Of course, you will find out that this pattern is not going to test only this fault, then it will test several other faults, but I am not coming into that. In this example, I have shown you the deterministic algorithm to test faults, which is called ATPG, which has to be done for difficult to test faults. So therefore, this is basically called sensitize, propagate and justify approach. In this case, there is a stacked fault, you are activating the signal to an opposite value. Propagation means you have to send the fault effect to an output path. Justification means all the internal signals you have to justify so that you get a proper primary input set. So basically this is the heart of all tests, that is you have to given us some faults, you have to find out what test pattern to apply. And as I told you, in traditional circuits our job was to get 100% fault coverage. That means some of the faults will be covering by the random manner and whatever will be remaining will be going by this ATPG approach, that you have to target each individual fault and you have to find out in this manner, so that we get a very high amount of coverage. But as when you will be moving to SOC NOC level paradigm, even this will be it will be blowing up, because the number of difficult faults will be also higher. Now it is a 3-level circuit, in this case it will be a very high level. This level means I am taking about these levels, this is 1, 2, 3, 4 level circuit. It will be a more higher level circuit, and things will again blow up because the number of stacked faults will be higher. Sensitize, propagate, justification will be difficult because there will be so many alternative paths to try and so forth. So there the optimization will be at a higher level of test, that is not even at the gate level, even at the black box level, like adder. I will consider adder as a block. I will consider maybe a multiplier as a block. This is actually called RTL level test. And we not even go for stacked faults. We also go for some abstract level of fault models like fault at the adder level, fault at the multiplexer level and so forth. Mostly they are motivated from the software point of view. So that will be the idea of how test patterns are optimized to handle large circuits. And also one important thing, now number of test patterns are becoming so large that we will have to try to compress them. Sometimes we will be slightly lowering down the coverage even, so that we can get a sufficient amount of quality confidence, but still with a very less amount of test time. So that will be the optimizations we will be talking when we will be going for optimization of the combinational circuit, ATPG, etc. Now everything was so much about combinational circuits. Now what about sequential circuits? What it will change? So in the tomorrow's preliminary lecture, as I told you, we have 2 preliminary lectures on the test. In tomorrow's preliminary lecture, I will tell you how things even become more complicated or more difficult when you go for sequential circuits. After that, we will start our optimization flow. Thank you.